lab number 9. So in this lab, we're gonna work on sequential circuits. So it actually has, this is the objective of this lab. Number 1, explore the behavior of a basic JK flip-flop. The second one here is actually you need to implement a simple finite state machine or clocked. This is the same name for synchronous sequential circuits. So let's start here. So here in the very beginning, let's make sure, yeah. In the very beginning here, I'm just explaining what is sequential circuits, what are latches, flip-flops. So from the lecture, you already, if you study the lectures, so you should know all of these things here. So here, this is for the pre-lab. In the pre-lab, number 1, you need to read these sections, okay? Number 2, we have a data sheet here. This data sheet 109. This data sheet, as you will see right now, inside this chip, it has 2 JK flip-flop, okay? Remember in the lecture, as I explained, in case of JK flip-flop, so if you have a flip-flop and you have here J and you have K, and then you have a clock this way, okay? So as I told you in the lecture, JK, when it is 0, 0, so it is no change. So Q will be the same. This is exactly what I want you to explore in this lab, okay? If it is actually 1, 0, so actually you are gonna make a set. If it is 0, 1, you are gonna make a reset. If it is 1, 1, so it's gonna make toggle. As I told you, toggle means if the flip-flop is storing 1, once you input this one, it's gonna become, if it's storing 0, it toggles, it becomes 1. All these actions are taken when the clock at the clock, either it is positive edge or negative edge, okay? Negative edge. In this case here, this is a positive edge, okay? So you will see, we will explore this chip, okay? You will see this chip has a reset, and we'll see right now. Also, we are gonna see if it is positive edge or negative edge, okay? But there is a small difference as you will explore. This is the normal JK flip-flop. It looks like that. However, as you will see right now, this flip-flop is actually, we have J and actually we have K prime. You will see it right now, okay? That means, so this is the input. It's not K. It has to be K prime. That means for no change, instead of 0, it has to be 1. For set, okay, it has to be, instead of 0, this one has to be 1. This one has to be 0, this one has to be 0. You got what I'm saying? You will see right now. So it's not like JK, it is JK or it is still JK, but the input you are going to input actually is the inversion of K. You will see right now. So it's just a very minor change. So here, this is from, you need to open. So if you stay on this one, you will you will see the hyperlink. You need to click on this hyperlink. You will see the data sheet for this flip-flop. Let's see what is written here. Number 1, it's written here, it is dual. Okay, so dual here means inside the chip it has 2 flip-flops, JK flip 2. Okay, this is number 1. Also, you can see here, as I told you, this one is not JK, it is JK prime. Is that okay? So that means it's everything like JK. The only difference is that the input, this input is actually K prime. You got what I'm saying? So you need to keep this one in mind. Also, you can see it is positive edge. Okay, from the lecture, you should understand what positive edge means. Okay, when the clock it changes from 0 to 1. This is at this time. The action is taken, okay? The Q changes at this time, okay? As I said in the lecture. On top of that, it has a clear and preset. Remember in the lecture, I didn't teach clear and preset in GK flip-flop. I think I explained it in G flip-flop, but I told you other flip-flops can also have clear and preset, and it's exactly everything. It's the same, okay? So here, you will see now. So here, I think it's negative. You will see if it is negative, active low, or active high. But as I said in the lecture, if it is clear, assuming you will see right now, I think, yeah, look here. Yeah, it is active. If when it is written this way, so it is telling you it's active low. Okay, that means for this pin, if you put 0, you actually clear. If you put 0 here, you actually set. Okay, and this does not, as I said in the lecture, this one does not happen at the clock. It happens immediately. Once you put 0, it's going to clear right away, okay? That's what I want you to explore in this lab. Let me see if, yeah, just, I just got this part from the data sheet anyway, okay? So as I told you, when you see bar this way, what it means it's active low. So if you want to clear, you have to input 0, okay? So they are inactive when they are high. Okay. Let me see here for sure. You have a clock here and everything following the hold time, and I think everything here is similar to what I explained. There is a very small point here you will need in this lab, and it's actually a question in this lab. So you remember D flip-flop, okay? So in case of D flip-flop, actually Q is equal to D, right? So if I put here 0, when the clock comes, you put here 0. If you put 1, 1 comes here. This is D flip-flop. So here, it's already answered here. It's a question, but it's already answered here. So if you have JK flip-flop, how can you make JK flip-flop? How can you make it D flip-flop, okay? So if you have normal J and K, okay? So what I can do if I put inverter this way, okay? And now this one becomes D flip-flop. Oh, how is that? I'm gonna tell you how. When D is equal to 0, so you put here 0 and then you put here 1. And from JK flip-flop, you know 0, 1 is gonna make actually reset. So you're gonna put here 0. So when you put here 0, you're gonna get 0 here, similar to D flip-flop, okay? Let's see the opposite. So if you put here 1, okay? So this one is 1 and this one is 0. And you know when J is 1, K is 0, you actually put here 1. So it's very clear. If you put 0, I'm going to get 0. If you put 1, you are going to get 1. This is D flip-flop. So this is the way you have to do it. However, because the flip-flop we have right now, you can see the flip-flop we have in this lab is actually, it's not JK. It's JK prime. So you can see it like J, and you can see it like there is an inverter here already. So you input here, whatever you input here. So you input here K prime, and this is J and K. You can see it this way. You got what I'm saying? Because it's not JK. What they did, they put inverter here. Again, you may, when you find maybe other chip has JK, it doesn't mean all of them this way, okay? But they put inverter here, okay? Because there is already inverter here. To make this JK flip act like D flip-flop, you just make a short circuit this way. You don't need to put this inverter. You understand what I'm saying? Because it's already there. Okay. So that means using the DC chip, if you just to connect J to the K prime, because that's what you have, K prime, you can make D flip-flop. Anyway, so this is how the chip looks like. So I need to know now. I told you we have two flip-flops, okay? For everyone, for sure, this is a chip, it needs a ground here. It needs 5 volt here. You have to do that, okay? To be able to use the chip. This number 1. Number 2. So now you can see here, this pin number 1, this is the clear for flip-flop number 1. This is the clear for flip-flop number 2. Is that okay? Okay. Let's see J. So this is the J here for flip-flop number 1. This is the J for flip-flop number 2, okay? Let's see K prime, because I told you this one does not give you K, it gives you K prime. So this is for number 1, this is for number 2. Great. This is the clock. You can see here, this is the clock for 1, and you can see the clock here, okay? So you can see the clock here is there is no bar. That's why it is actually, it's gonna become positive edge, okay? For preset is here, and the preset is here. For Q and Q prime, yeah, they are here. Let me clear everything. Okay, so here This is for the first flip-flop. This is for the second flip-flop, Q and Q prime. Okay, so you have everything here for two flip-flops. So this is the truth table we have here. You will find this truth table is exactly similar to what I explained before. I'm going to explain it again, but the only difference is this is K prime. So you have to consider this. Okay. So let's see. Number one, as I said also in the lecture, let's see the first one here. So if you this is low, so this is low, and then you put here high. So immediately, if you see something like that, it's gonna make a preset immediately. So I'm not gonna wait. That's why there is X here. So this X means I'm not gonna wait for the clock because this happens immediately. This one, regardless what is J and what is K, is what's gonna happen here is you are doing a set. Okay. For sure, always Q prime is opposite of or the toggle of Q. Now let's look at the second one here. The second one here is if I put here high and I put here low, that means you are triggering clear. Okay, same thing is gonna be. I'm not gonna wait for the clock. It's gonna happen immediately. Okay, immediately you are gonna have here low and high. So so these two can be used for set and clear. Okay. The next one, which should be a forbidden case, it should not happen when you put low here and you put low here. For sure, doesn't make sense. You wanna clear and you wanna set at the same time. So this is like it's gonna become like a forbidden case. So this case here, this case forbidden case. Okay, so you should not use it. But in case if you do it, I think the data sheet is telling you what you are gonna have high or whatever. Anyway, so this case you should not do it anyway. Okay, so now this is the normal operation here. So this part here is the normal operation. And this normal operation, as you see here, high and high for preset and clear. So there is no preset and there is no clear. This is the normal operation we have before. However, keep in mind, K is flipped. So as you see here, this one, so here, always this action, what this means when you sit in this truth table this way, it means the action will be taken at the rising edge. Okay. Here, when we put X here, it's so regardless what is the clock, or regardless if the clock is an edge, a positive edge, negative edge, high or low, doesn't matter. Okay. So let's see. So now I'm gonna put here low and low. Is that okay? Remember, this is K prime. That means because this one is low, that means it is high, K is high. So I can make another column here for K. K is high. So as you know, when J is low and K is high, so in this case, it's gonna be low. You are gonna put zero, store zero. Okay. Let's see the next one. Here you put here high and you put here low. So actually, is this low? K is going to be high. K is going to be high. So when it is high, 1, 1 is actually toggle. Okay. Let's look at the next one. Here it is low. And this one, K prime is high. That means K is low. Low and low, 0, 0. That means no change. So Q0 will be the same. Q prime will be the same. No change. Okay. Let's see the next one here. When you put high here and high here. Remember, this high is actually K is low. As you know, for GK, when it is here high and here low, you're actually making a set. Okay, as you see here. Yeah, the last one here. What I want to tell you here in the last one is when the clock is no change. So no change when the clock is low. Okay. I don't know what this means, but I think what you want to see here is if there is no edge, if there is no rising edge, it should not work. Okay, so I'm just surprised why they say low here, because it's the same thing if it is high. So again, if you have a clock like this way, the action will be taken at the rising edge. Okay, so when it is 0. Still no action. When it is high, also no action. It has to be a rising edge, and this is expressed here. Okay. So the first part in this lab, I want you to use this chip just to get used to JK flip-flop and just explore the truth table. You see, I'm saying toggle. You will see if it is gonna do toggle or not. I'm saying it has to set or no change. That's what I want you to explore. Okay. So I'm gonna, because this lab, as I told you, it has two parts. One part is about a sequential circuit, analyzing a sequential circuit. I'm gonna talk about it, but let's finish the first part first. So in the first part here, you are gonna use the J-key flip-flop using one of the J-key flip-flop you have. You can use any one of them. You have two, but we need only to use one, okay? Set the input signal to do the following things. Here, number one here, using J-key flip-flop, set Q to low on a rising edge. So here, this is the thing, first thing you have to, so you need to know what input I have to input here, what values I have to put it in G and K in order to make Q is equal to 0. Okay, it's already in the table here. So I want you to do it and to check it. Just I want you to get familiar with the use of flip-flop, okay? Second one here is, the second one, asynchronous. I'm going to tell you what it means. Set Q to 1. So I want Q to be 1 asynchronous. Usually when I say asynchronous, I mean in digital systems, I mean there is no clock. Okay. So here asynchronous means, because this action, I think I'm going to repeat the same thing again, and I'm going to say on a rising edge. Yeah, look here. So look what is the difference between this one here and this one here. Okay. So let me clear this one. Look here, this one, and actually this one here. Yeah. So here you are going to set 1. Here you also store 1. But here you are going to store what? 1 at the edge. Okay. So you have to see what value you have to input in J and K prime in order to get 1 when edge comes. Okay. But in the other one here, asynchronous. So in asynchronous here means immediately without a clock. You don't need to wait for a clock. Okay. So for sure, this means you have to use the preset for this one. Okay. So let's see the other thing is here. Same thing here for yeah. I want here on the rising edge. I want to remember the same value, means no change. So you have to see, you have to make no change here. So you need to see what input values they are gonna make no change. Okay. For this one, in order to be okay, let me see next one. Next one here, I'm asking you to make a toggle. Okay. So you need to see, for example, you have a flip-flop, the output is already 1. Okay. Once a clock comes, it's rising, I'm sorry, rising. Once a clock comes, it's gonna toggle. That's it. That's what I want you to see. Asynchronous, 0, asynchronous. That means you need to make a clear, okay? By the way, how can you implement the clock? Okay, if you connect the clock to a screw like this one, you are not gonna have a control on when it's gonna happen, because what's gonna happen here, I mean, action will be taken here all the time, here and here and here, okay? So I think one way to do it is using a switch to implement the clock, just to have control on when it happens, okay? So the way you can do it, because this is a positive edge, this is one way to do it here, this way. It has to be this way. Is that okay? So I can connect this one, for example. I can connect this one. I can use a resistor this way, connect it to ground this way. That means all the time it is 0. Okay. And then I'm gonna make a switch this way, and then I'm gonna connect it here 5 volt. Is that okay? So normally it is 0, and then once I connect the switch, I'm gonna make it 1. By this way, it's like you manually, I'm gonna input a clock manually. Okay. So what you have to do, I think this is the best way to do it to understand this this part. You just select what values you have to put for JK or for clear or for reset. Once you do that, if you don't need a clock, this is gonna happen immediately. If you need a clock, so you can just connect the switches this way. Okay. And then once you open it again, so this is the main thing. So it's always 0. Okay. So once you connect the switch, it becomes high. Okay. And then once you disconnect the switch, it's gonna return to 0 again, and so on. Okay. I think this is the first part of the lab. The second part of the lab is about how can you analyze a sequential circuit. I already explained one example much more difficult than the example I give to you here. So, and how can you make a state table and state diagram? Okay, I can explain it now very quickly. So actually, I'm giving you this circuit as you see here. I'm sorry. Okay. So I want you to implement, as I said in the lecture, the state table is similar to the truth table, okay, in combinational circuits. Okay, so it should describe how the circuit works. But here it is here because it's in sequential circuit. It's it's different from combinational because the output does not only depend on the input but also the current state or the value of the state. Here means the value of the flip-flop you have. Here you have only one flip-flop, so it should be very easy. But in the example I taught in the lecture last time, there was two flip-flops. Okay. By the way, this circuit here is very similar to another example you have. Yeah, this in 550, this example. So I already explained one example. So there are three examples I'm gonna explain. So it's just almost, as you see here, almost the same thing, but it's even more easier because I just deleted this part and consider this X here. That's it. So this one is very close to this one. Okay. So my suggestion is try to understand this example first, and I'm going to explain it tomorrow. And then once you understand it, the other one will be, it's trivial. Okay. So, all right. So now, so here what I'm asking you to do is complete the circuit diagram. So we're going to use here D flip-flop. So the question is that now do you have D flip-flop? Okay, you can check if any chip you have has D flip-flop, you can just use it. It's totally fine. If you don't have, I told you, you can use the same JK prime you have, and that's just to connect them together, and now it becomes D flip-flop. Okay, so you can use D flip-flop this way. And then you need to connect XOR this way, and the output here has to come to here this way, and you have only one input here. So as you see here, we have one input, we have here one output here, and one state, okay, because it's one flip-flop, okay? So here I'm asking you, you need, by the way, the synchronous, you may be confused when you see the term, this term, which is finite state machine, or sometimes we call it FSM, finite state machine. Don't be confused. Finite state machine is actually synchronous sequential circuits. That's it. Any sequential circuit that's synchronous again means use clock. It is FSM. Okay. You can tell from the name finite state machine because it has a finite number of states. And again, states here means the values of the flip-flops. Here, because I have only one bit, so we have only two states, either 0 or 1. You got what I'm saying? Anyway, so and then here I'm asking you to implement. So here I'm asking you, you need to find input output table, state table. Also, you need to find state diagram. You can implement it using the digital tool. So yeah, maybe I'm gonna explain this example in the lecture, but I'm gonna go through it quickly because it's very similar to the example what we have here in the lab. I told you we're gonna just delete this one here. And instead of having two inputs, we're going to have only one input X. So if you look at this table here, we have two inputs, X and Y. So I'm going to cancel Y. There is no Y. Okay. And in this case, as you see here, I'm going to have two inputs instead of three. I'm just explaining the difference between this example and what you have to do. Okay. So in this example, you have three. You have three here. Okay. 3, which is the state and two inputs. You have 3. That's why when I created the table this way, I should have 8 different values. Okay. Our example here, it's very simple. Just we have A and we have X. Okay. Same thing. You need to put the present states similar to the example I explained in the lecture. I'm going to explain more example, but believe me, all of them are the same. If you just understand one of them, it's just if you understand the steps you have to follow, all of them you have to use the same steps, okay? And then we have here the next state at time t+1, as I told you before. Same thing here. I can have here. Let me clear everything. You are gonna have a x and then at+1. Okay. So now these are the inputs. So you have to put all possible cases here, which 0, 0, and then 1, 1, 0, 1, 1. These are all possible cases we have. Is that okay? And then you can see when, forget this one, x is here, okay? So now if A is 0, okay, so here you have to 0, x is 0, okay? So now because they are equal, so the output here, I think it's 0, right? In XOR, you can correct me, okay? So in XOR, if it is equal, you get 0. If it is not equal, you get 1. So I'm going to get 0 here. So because this is a 0 here, what is the value here? It will be the same. So next state will be 0 for this input, okay? Let's look at the second one here. We have 0 and 1, okay? So here, let me see how can I do this. Let me erase this one here. Okay, good. So cancel this one. Okay. So, okay, let me need to go back. Okay. So now, if you have here x here is 0, x is 1. Okay. I told you they are different because they are different, so it should be here 1. So, and 1 should come here, so this one should be 1. Okay. Same thing here. They are different, right? So it has to be 1. They are the same, should be 0. Okay. That's it. So this is a state. So now, how can you draw a figure here? Okay, so what you have to do, because we have only 2 states, 0 and 1. Okay, 0 and 1, 2 states. Okay, you can see in the first record here. Okay, if you are 0, okay, and x is 0, next time you will be at 0. That means it's gonna become this way. Here x is 0. That means what this means? It means if I'm in state 0 and x, this is x. X is 0, I'm gonna stay in state 0. And that's exactly what happened in this row here. Let's look at the second row. If you are 0 but x is 1, you are gonna go to state 1. So yes, you are gonna go to state 1 when x is 1. Okay. So if you are in state 0, again, state here means the value of the flip-flop. If it is 0 and x is 1, you are gonna go to 1. Let's look at the second one, next one here. If you are in state 1, which is A, state 1, x is 0, you are gonna stay at 1. That means it's going to become this way. If you are at 1 and x is 0, you are going to stay at 1. Okay. The last one here, if you are at 1 and x is 1, you are going to go to 0. Sorry, x is 1. Yeah, I'm going to go this way. Anyway, so again, you guys, what I'm doing here is exactly same thing. It's the same thing I did for the truth table for the combinational. But here I'm doing it in a different way because sequential circuits are different from combinational circuit. To describe how the circuit works here in the sequential circuit, it has to be in a different way. So truth table is not valid here. Okay. Anyway, so then here I'm telling you, you need to implement this circuit, you need to test it, and then you need to draw this timing diagram. Okay, so here in this timing diagram, it's just very simple. So this one is similar. This is exactly, you can get even the result is from here, from timing here, from as I explained here. Okay, so you have here, as I said, you have 0 and you have 1, right? So when x is 1, you are going to come here. When 0, I'm going to stay here. When 0, I'm going to stay here. When it is 1, I'm going to come back to here, right? So if you are at state 1 and x is 1, you are going to move. These transitions happens at the rising edges, okay? So I just want you to draw this one, okay? So what happens here in the very beginning, x is 0, okay? X is 0. And so action will transition happen only here at the rising edges, as you see here, okay? So here, when x is 0, you can assume originally you are 0, okay? At the D, sorry, not D. At A here, originally you are 0, okay? So when A is 0, look at this one. This one can describe everything. That's why I'm telling you, this is like a truth table. This one is telling you the behavior of the sequential circuit. So what this one is telling you is, when you are in state 0 and then x is 0, are going to stay in 0. That's exactly this case, right? Assuming A will start from 0 and x is 0. So in this clock, we're gonna stay at state 0. Is that okay? Now let's look at this one. Now x is 0, and x is 0 here, and sorry, you are in state 0 right now, and x is 0. So you're gonna stay in state 0. Is that okay? For this one, you can consider it like high this way, okay? Okay. So now, because this one is high here, and this one now is 1, right? So x is 1 now, okay? So try to make it this way. Okay? Yeah, you can make it this way. So when this one is high, okay, that means now x is 1. Okay, x is 1. When x here is 1, so what's going to happen? You are going to move to state 1. So now we are going to move to state 1, right? State 1. Okay. And now in this one here, it becomes 0 because it is 0. Because you are already in state 1 because it's 0, you are going to stay in state 1. Okay. It is 0, you are going to stay in state 1. X is 0, you are going to stay in state 1. X is 0, you are going to stay in state 1. Okay. Again, assume this one is like something like that. Okay. So now here, x is 1. So now, if I'm in state 1, x is 1, I'm going to go back to state 0 again. Okay. Okay. Now, x is 1, right? So x is 1, so you are going to move. Every time it is 1, you are going to move from one state to another. So I'm going to move to state 0. State 1, yeah. So now it is 1, so I'm going to move to the next state 0. If it is 1, so I'm going to move to state 1, and so on. Anyway, I think that's very enough for this lab. So here in this lab, I'm asking you, how many flip-flops are needed to implement a finite state circuits with 11 states? Okay, remember, if you have n flip-flops, which means n bits, okay, you can have up to 2 to the power of n numbers or states. You get what I'm saying? So if you have n flip-flops, for n flip-flop, you can have up to 2 to the power n states. It doesn't mean you have to use all the states. You got what I'm saying? But this is up to. Maybe your circuit is not going to use all the states. I think there is one example is talking about this one. Here I'm asking you, how do the DJK flip-flop behave when both preset and anti-clear signals are asserted? Okay, when it is high and high, you can. You can. I told you this is a forbidden case. You should not do it. You can do it in the lab and see what's going to happen. If you come at the clear here, and you asserted here means it's active. It means low and low. Okay. So if you come to the preset and also the clear, you put 0 and 0. Okay. So next one, I already answered it. How can you use the JK to make it D flip-flop? Okay. Also, how can you make it like T flip-flop? T flip-flop. So think about it. What are the difference between a truth table and truth table and input-output next state table? Okay. What is the difference between them? Okay. Actually, they are doing the same thing, by the way. Both of them are describing the behavior of logic circuits, but this one for combinational, the other one for sequential. Okay. Next, include a photo of your circuit, your breadboard, whatever. I think this lab just very easy. You need to, it's a practice on flip-flops and also a small sequential circuit. Okay, good luck and thanks.